You may have noticed that the previous video shut off kind of quickly. That's because I had made an algebra mistake, so I had to truncate that video and start over again. So this is kind of the last step we read in the previous video. We had found the height of the function at the point x sub I. And then we can combine the like terms 1 and 2 to get 3 plus 4 over n I plus 4 over n squared I squared. And this is the height of the ith rectangle. So the area of R sub I is going to be the height times the base. So that's f of x sub I times delta x. And remember, delta x was equal to 2 over n. So we have 3 plus 4 over n times I plus 4 over n squared I squared multiplied by 2 over n. So if we distribute, that gives us 6 over n plus 8 over n squared I plus 8 over n cubed I squared. And that's the area of that one rectangle. So if we want the upper sum, we have to add together the areas of all of the rectangles. So I'm going to add together the area of R sub I as I goes from 1 to n. So that's the sum I equals 1 to n of 6 over n plus 8 over n squared I plus 8 over n cubed I squared. Now let me remind you of some formulas that we learned in the introductory videos to this section. We learned that the sum I equals 1 to n of 1 is equal to n. We learned the sum I equals 1 to n of I is n times n plus 1 over 2. And the sum I equals 1 to n of I squared is n times n plus 1 times 2n plus 1 all over 6. We're going to use these formulas to rewrite this expression. The next few steps are going to involve a fair amount of algebra, so hang with me. Let me just recopy this to the top, and then we're going to start plugging those guys in. Okay, here we go. So first of all, I can distribute the sum over these three terms so that I end up with three separate sums. The sum I equals 1 to n of 6 over n plus the sum I equals 1 to n of 8 over n squared I plus the sum I equals 1 to n of 8 over n cubed I squared. Now in the first sum, my index of summation is I. I'm summing with respect to I. And this expression doesn't have any i's in it. So I can factor this 6 over n to the front of this sum. So I have 6 over n times the sum I equals 1 to n of 1. In the second sum, I do have an I, but it's multiplied by 8 over n squared. So the 8 over n squared can be factored to the front. And in the last sum, I have 8 over n cubed times I squared. The I squared has got to stay inside because that's my index of summation. But the 8 over n cubed can be factored out front. Now look at these sums we have. This first one involves the sum I equals 1 to n of 1, which is exactly the first formula over here. The second sum involves the sum of I, which is the second sum. And the third one involves this sum. So one by one, I'm going to substitute n, and then n times n plus 1 over 2, and finally, n times n plus 1 times 2n plus 1 over 6 for these three sums. So the first sum gets replaced by n. The second sum gets replaced by n times n plus 1 over 2. And the third sum gets replaced by n times n plus 1 times 2n plus 1 all over 6. And now let's do some algebra. I'm going to simplify each of these terms. And then so that we can work with it a little easier, I'm going to get a common denominator and combine. So in the first term, I can cancel the n's. In the second term, I can cancel one n from top and bottom, and also 2 divided into 8 is 4. In the third term, I can cancel an n from top and bottom, which will leave 2 n's on the bottom. I can also cancel a 2 between the 8 and the 6, leaving me with a 4 on top and 3 on the bottom. So let's just look at what we've got. We have 6 plus 4 times n plus 1 over n plus 4 times n plus 1 times 2n plus 1 all divided by 3n squared. So looking across, I can see that my common denominator, least common denominator, is 3n squared. So I need to multiply this term by 3n over 3n. And I need to multiply this one by 3n squared over 3n squared. So that'll give me 18n squared over 3n squared plus 3n times 4 is the same as 12n. And I'll multiply the 12n times the n plus 1. So that gives me 12n squared plus 12n over 3n squared plus, here in this last term, I have a 3n squared on the bottom. And let me just FOIL out this pair of binomials. I'll leave the 4 and distribute it later. Multiplying this out, I have 3n squared plus n plus 2n is 3n. Oops, sorry, that's a 2n squared. Plus 1 times 1 is 1. Now let's put these fractions together. My common denominator is 3n squared, and on top I have 18n squared plus 12n squared plus 12n. And finally, distributing this 4, I pick up 8n squared plus 12n plus 4. And let's combine like terms on top, and we'll have our expression for the upper sum. That's 18n squared plus 12n squared plus 8n squared is 38n squared. 12n plus 12n is 24n, and I have a 4. And that's our formula for the upper sum. Now let's check and make sure that this seems reasonable. Notice that this formula only involves n, which is the number of rectangles we have. So, for example, for n equals 4, the upper sum is going to be 38 times 4 squared plus 24 times 4 plus 4, all divided by 3 times 4 squared. If you put that in your calculator, you should get 14.75. And notice over here, I'll let this number up so that you see that we're getting the same thing we did before. So this formula gives us the upper sum for 4 rectangles. And similarly, if you take n equals 5 and substitute it into this formula, you should do it. Plug in 5 for each one of these n's. You're going to get that the area is equal to 14.32. Now, we put a lot of algebra or algebraic investment into getting this formula. But notice now that if we wanted to use a big number, for example, n equals 100 rectangles, we don't have to go through all the sums separately and make the tables. We can just plug in to this formula. We'll get an upper sum, if my calculation is right, of 12.75. So notice, as predicted, the bigger the n, the smaller the upper sum is getting. So the idea is, as we let n get bigger and bigger, the lower sums and the upper sums are squeezing the true area in the middle, just like the squeeze theorem. So if you were to take this expression and let n go to infinity, then that should give us that point where the upper sums and the lower sums meet. So the true area under the curve should be equal to the limit as n goes to infinity of the upper sum. And you should get exactly the same limit for the lower sum. Well, here's the formula for the upper sum. 38n squared plus 24n plus 4, all divided by 3n squared. But look at this. We're taking the limit as n goes to infinity of a rational function where the degree of the numerator is the same as the degree of the denominator. We call rational functions like that balanced, and we learned that we could find the limit by just taking the ratio of the leading coefficients, which is 38 over 3. And 38 over 3 is indeed the exact area underneath that parabola between x equals 1 and x equals 3.